All right, it is now noon Eastern time, so we will go ahead and get started. My name is Heather Versilla. I'll be hosting the webinar today on the evolution of reliability-centered maintenance. I am part of the marketing team here at Test Oil and have been here for almost 10 years now. I have my CLS and I would like to tell you a little bit about Evan Zabowski, who is our presenter for the webinar today. Evan is a certified lubrication specialist with diplomas in chemical engineering and fourth class power engineering. He has extensive experience training tradesmen and professionals in a variety of fields, including lubrication fundamentals, contamination control, condition monitoring, RCM and FMEA, and used oil analysis. And he's been a member of STLE for over 18 years, serving as the chair of the Alberta section for 8 years, and has also been an instructor of the condition monitoring course. He's also now on the board of STLE, and he has served as the editor of TLT magazine, as well as the STLE Alberta section's Basic Handbook of Lubrication 3rd edition. And he's also contributed as one of the editors for the STLE and CRC's Handbook of Lubrication and Tribology Volume 2, which is on theory and design in the 2nd edition. In addition, Evan's published several technical papers, and he's also been a member of API and ASTM over the years. Evan is Test Oil's senior technical advisor. He is the person that instructs the majority of our training courses and does a lot with our webinars, and is a really great source of information. And as we go through this webinar, if you have any questions, please feel free to put them in the chat or the questions section. And once we get towards the end of the webinar, Evan will have time to answer some of those. Anything that we can't get to, we'll email you in response, and there will be a recording of this webinar that is emailed out to everyone. So if for some reason you have to step out or you're coming in late, you'll be able to see the webinar in its entirety. With that, Evan, go ahead and take it away.
All right, thanks, Heather. So yes, today's webinar is about the evolution of RCM. So essentially what I'm going to walk us through is a little bit on probability of failures. We're going to discuss most predominantly the bathtub curve and kind of why it doesn't work very well. But that's what led us to RCM. We went through 3 generations of thinking when it comes to how we thought things failed. We're currently on this 3rd generation and have been for quite some time. But that spawned some new thinking in terms of maintenance strategies. And so we'll go through the 4 primary ones and then finish up with our discussion on reliability-centered maintenance, or RCM. So it's more or less going to play out kind of like a timeline. We'll go through some of the major events that led to the forming, I guess, if you will, of RCM as a new strategy, but show how it's really an amalgamation of all strategies and not like some newfangled way of doing things. So with that, let's get started on probability of failure. Basically, when we first got into paying attention to how machines operated and whether or not they were going to fail, we thought things went one way. And this started in about the 1930s and didn't last very long, but probability of failure was seen one way and one way only, and it was that things simply wore out. That the longer you use them, the greater the chance was that they would eventually fail, but most things had like some critical point where after so many cycles or hours, it was expected that the probability of failure was increasing significantly. So this is what got us started on paying attention to the probability, and it quickly evolved into a newer way of thinking that lasted for about 30 years. And this was what sort of spawned the bathtub curve, which we'll get into in a second, and we'll talk about why it doesn't work very well. But the interesting side of it is that they viewed probability 3 different ways. They had what they called an early, a constant, and a wear-out curve that they could plot the probability of failure on. Now, over the years, we've kind of renamed these ones, and you might be a bit more familiar with the term infant mortality rather than early. And I do prefer the term random more than constant because it does imply a little bit of the unpredictability to a constant probability of failure. And wear out has been renamed time and condition dependent because it's not just a time factor, but sometimes it's a change in operating conditions, operating environment, things like this. So these three curves essentially were sort of a new way of looking at things by adding in early and constant to the already existing wear-out curve. But somebody then looked at this and said, you know, you can put them all together. So let's give you a visual on that. Here we have the early, the red curve, the constant, the green curve, and the wear-out, the yellow curve. But if you add all three together, you'll get that blue curve, which is the bathtub curve. So let's just go through each of these four curves quite briefly, but just lead us up to the discussion about the bathtub curve and why it's so popular, but why it doesn't really work. Now, the infant mortality curve, the one that used to be called early, means that you have a high probability of failure when the parts are, or the machine is new, and that probability of failure drops significantly and essentially never returns. But basically, if you can get over the initial installation, the initial commissioning of that part, you shouldn't expect any future failures to any great degree. Now, why we call it infant mortality is because one of the leading causes to these failures happen within the first few hours, and that is often due to an installation error or an operating condition not being met, but sometimes as well it can be due to defects in the parts themselves. That's a lesser side of the infant mortality curve, but it's often one people go to right away. You know, you put a brand new part in and it fails, you immediately think there's something wrong with the part. Often it's actually something wrong with how you installed it or how you commissioned it, how you got it up and running to begin with. But essentially, the infant mortality curve is just saying, if you can get over that initial start, the probability of failure should go down and, like I said, never return. The other curve, though, the green one, the constant, or like I said, I prefer the term random, means that you don't have a very low probability of failure, but you also don't have a very high probability of failure. You just have a moderate probability of failure, but it's just as likely to fail today as it is to fail tomorrow. You simply don't know when, and you have no indicators throughout the life that it's more likely or less likely to fail at any given moment. So that's why constant makes sense because it's a flat line, but random is a bit better of a word because to us, anything that can occur at any point in time seems like a random occurrence. But this means that you have no way during the life of the expected component to know whether or not the probability is going to be any higher or lower. So it's the least predictable, if you will. But the last curve is the one that we already had, and this is, you know, not really changing in any great way. It does show more of a slope to it at the beginning, that it's not necessarily flat, 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 and then sudden inflection at the end, but it says, look, the probability of failure will be low upon initial installation or initial commissioning. You should be able to run for a while, and then it will slowly start to increase over time as you build up more hours, more cycles on that component. But then again, there still will be some type of inflection, and the rate will increase significantly. And these are usually referred to as machine life. If you're into bearings, it's, you know, the L10 life, things like this. There's kind of that book value that you expect that, look, it should last this long. The probability of failure will be low during that time, but after that book value time, you will expect the probability to be significantly higher. Now, as I said, if you add up all four of these, you get this blue curve here, the bathtub curve, and the idea is that it's a combination of all three. And the problem is that not everyone's aware that you must meet all three criteria to say something does or does not fit the bathtub curve. But the nice thing about the bathtub curve is that when things fit the bathtub curve, generally some form of condition monitoring will be useful at predicting some of these failures, particularly the ones that would be represented by the yellow curve. But no real form of condition monitoring can always catch every type of early failure, the red curve, so it gets difficult to predict those ones. And then anything through the middle, it kind of depends again on what type of failure it might be. So we rely on condition monitoring, but the bathtub curve shows us that really only part of that curve will really truly be addressed by it. And why the bathtub curve doesn't work, I'll show you in this next generation of thinking. Where we are today is this third generation, which ultimately is made up of 6 curves rather than 3 curves or previously 1 curve. And of the 6, we actually have 4 that we already had. We have your infant mortality, we have your random or constant, and we have the wear out, the same three that were in the second generation of thinking, but we added in bathtub as a fourth one. So it is a separate curve, not just merely looking at a combination. What we added in, though, were the couple in the middle. We added in a fatigue curve and an initial break-in period curve. Now, these 6 curves essentially fall into 2 categories, the first category being those that are age-related. By saying that they're age-related, simply implies that the failure probability increases over time, or that at least after a certain time factor, the probability increases substantially. So, of course, the wear-out curve fits that description perfectly. The bathtub curve will also fit it because it is made of the wear-out curve, but that's where we added in fatigue. Fatigue is just a constant but slowly increasing probability of failure over time. The other 3, on the other hand, are what we call non-age related, meaning that they don't increase over time, and specifically, there is no sharp increase after a set number of hours or cycles. So time does not seem to be a factor. Now, infant mortality, of course, fits that perfectly. Random more or less fits it because there is no increase at any point in time along its curve. But then the break-in curve is more or less the inverse of the infant mortality curve, saying, look, the failure probability is very, very low upon initial installation or commissioning. It will increase, relatively increase substantially, but then it levels off and it's never particularly high. So with these six came out of a document referred to as the Nolan and Heap report because it was printed by a couple of engineers, last name Nolan, last name Heap, but it's more commonly known in some circles as the book Reliability-Centered Maintenance, which is, of course, the point of our discussion here. Now, when these engineers were putting together this monumental paper and categorizing failures in these 6 categories, they grouped their own data into these 6 categories and shared it. What was interesting is as they went to publish this, they had found that another airline over in Sweden also collected similar data and grouped it in the same 6 categories. And what was really remarkable about this is that the data agreed to within 1 or 2% for almost all values. I mean, you couldn't ask for more replicable data, meaning that they were able to replicate it almost perfectly using a completely different fleet of airplanes. So let me show you the data that they collected. So this is all aviation based, and the blue bars here represent what Nolan and Heap came up with. They were part of United Airlines. The orange bars are from the airline in Sweden. And what they found was, if they grouped all their failures, they found very, very few fit the bathtub curve. In fact, less fit the wear-out curve, and hardly any fit the fatigue curve. What they did find, though, was some would fit the initial break-in curve, and some fit the random curve. But by and large, as you can see, most of their failures, they felt, could be classified under the infant mortality or the early curve. And that was quite remarkable because that really changed how people thought of things. I mean, we started with the wear-out curve, then we added in the random and the infant mortality. But what we realized was most things were this infant mortality. And even after we added in the other 3, we didn't really see any sharp increases there. So this started to shake things up in industry. And just to share with you some more data, because it's kind of fun to look at what people come up with, here's a couple out of the Navy. And these are for different maintenance groups within the Navy, but again, they kind of replicated some of the same points, is that almost nothing fits the bathtub curve. What they found was similar values in fatigue and initial break-in, but they took away a lot of the infant mortality data and they classified it a little bit under wear-out, but most of it under random. So if you go between the 2 sets of data and ask yourself, what are the 3, if you had to pick 3 out of 6, what are the 3 most common failure curves that the data actually fits? And your answer is going to be infant mortality, random, and wear-out. Exactly where we were with the second generation of thinking. So even though we're now on this 3rd generation, we've added in 3 other curves, what we've discovered is they don't represent much of the data. And in fact, the bathtub curve is about the worst. And the reason it's so popular, but the reason it's also not good, is that so much data seems like it fits the bathtub curve. because anything that can be classified under infant mortality fits the first part of the bathtub curve. Anything that fits wear out will fit the last part of the bathtub curve. And as this example shows, anything that fits in random would fit the middle part of the bathtub curve. So many people can find things that fit part of the bathtub curve, and therefore they think the bathtub curve works. But to truly be a bathtub curve worthy entry for data like this, you have to show a part or a machine that has an extraordinarily high probability of failure when new, but as it breaks in, it goes down. As it runs for many, many hours, it doesn't change, and then suddenly, after a certain number of hours, it increases again. And there truly are very few items out there in industry that fit the entire bathtub curve. So really the bathtub curve doesn't work. The bathtub curve is just a popular way of summarizing the three most common curves, but the thing is they're all three independent from each other. We shouldn't try and push them together. So I've given you a little bit of a hint here about RCM, and just suggesting to you it was one of the things that discovered this, but let's actually walk ourselves through the maintenance strategies and the timeline for RCM. So when I say maintenance strategies, generally speaking, what you're trying to say is there are four, and we jokingly call these things the 4 Ps, because we have reactive, preventive, predictive, and proactive, and we jokingly call reactive percussive, meaning if it makes noise, go fix it. But of these are the primary ways of dealing with failures. And as I list here, a common misunderstanding when you're trying to define these is you're thinking about the person. You're thinking about you and how you relate to that word, not how the failure relates to that word. So the sentence I give you there, just to show you how confusing it can be when you use the word on yourself rather than use the word on the failure, is that are you being proactive when you react to a condition, predicting it will fail and then prevent it from occurring? So see how I use all 4 words in the same sentence? It doesn't help, right? We have to think about the word as it applies to the failure. Otherwise, we'll just trip over ourselves in trying to define these. So the simple way, and I'll get into more detail, but the simple way of looking at it is, again, think about how this word applies to the failure. So if you're reacting to the failure. So if it broke, you're fixing it. Now, when you're preventing, in terms of preventing the failure, so it wasn't broken. There has not been a failure. So you fix it anyways, right? You fix it ahead of the failure. Predictive means you have a way of knowing it's about to fail. You have some condition monitoring tool, some signs, some symptoms. And if it's not broken, you don't fix it. But if it's about to break, you will fix it. And proactive is the trickier one there. Proactive is doing something in advance. Now, how is that not being predictive or preventive? Proactive is learning from a failure and fixing it going forward so that it never fails the same way twice, right? It's the fix it right the first time kind of mentality. So that just gives you a brief overview, but let's get into a bit more detail so we really understand these ones. So reactive maintenance is commonly known as run to failure because that's how we're treating the failure. We're reacting to it. It has to fail first, and then we allow it to be repaired. So this type of maintenance is done as an as-needed basis only, and as needed meaning the machine has probably stopped functioning. So it has some merits. You could do this on things that are non-critical, and if they're inexpensive and don't have much risk to any other machinery around it, that might be a suitable way of doing things. I'm not saying it's wrong. I'm just pointing out that it does seem like a bit of a tricky way to run your maintenance program. I mean, the joke being that if you don't plan your machine's maintenance, it will plan it for you. That kind of holds true with run to failure, in that you will have to do it when it tells you to because it will probably not be functioning. So the advantages to doing reactive maintenance is you're not spending a lot of money on parts and labor because you don't have to on a day-to-day basis, and you generally don't need as much staff. The downside, however, is that when you need it, now you're hot-shotting parts in, you're calling in for overtime, there's a lot of other aspects to this that start to really greatly increase your cost. What you also sometimes suffer is a bit of a hazard in that what happens if it fails unexpectedly? Is there a safety concern? Will people be harmed by the way this machine suddenly shuts down? Will it trip something in the system that can cause, again, a cascading effect to invoke some safety issues? Will it cause any what we would consider collateral damage, damage to nearby machinery or downstream machinery because of the way it abruptly stops functioning? And of course, above all, the staff you do have on hand, you're not using very efficiently. So it has definitely some downsides. The improvement over reactive maintenance is to go up to preventive maintenance. Now, preventive maintenance is what we call either an interval or time-based maintenance, meaning you do things based on a schedule. So if you think about your own house, it could be when you change the batteries in your smoke detector, when you change filters on your HVAC system. These are things that you do based on a schedule, right? Every 6 months, every time the season changes, something along those lines where you don't have any real driver to say, I checked my batteries and they were low. I checked my filter and it seemed a bit dirty. You just say, look, I do this based on this timeline and it will make sure I don't have any problems. And funnily enough, one of the best examples I can give you of this that most people don't always think to first is an oil change in a car. An oil change in a car is absolutely an interval or a time-based measurement. Right? If you change your oil every 5,000 or 10,000 hours, whatever it happens to be, 5,000 or 10,000 miles, that is an interval, right? You don't know that at 10,000 miles, the oil needs to be changed. You don't know that it does not need to be changed either. You just say, it's been 10,000 miles, I should take it in for an oil change. Right? That's what we mean by an interval or a time-based measurement. So parts or maintenance is done based on some type of schedule. There are no measurements directly impacting that decision. So where this seems more appropriate is on things that are a bit more expensive, but have a lot of low-cost parts that you can use to maintain them. So that's why an oil change makes a good example, because you can have a $20, $30, $40, $50,000 car, and it's under $100 to change the oil. Right? It's a very inconsequential cost to the total ownership cost of the vehicle, and it gives you peace of mind. Now, what's interesting about preventive maintenance is if I go to this NASA document you see cited at the bottom, they estimated that preventive maintenance is a little bit cheaper overall than doing reactive maintenance. So even though you're replacing parts, maybe not when they necessarily need to be, the overall cost of your program is a little bit lower. Now, the advantages with preventive maintenance is that you are hopefully having lower downtime costs because maybe you're having less downtime. It's also very easy to forecast your parts and labor requirements because you're doing this all based on a schedule. And I say this with all seriousness, but I know some people take it as a bit of a joke, you have better coordination between maintenance and production. Now, those of you who work in maintenance and have to deal with production will often tell me that no, production never wants to give up the machines for maintenance, but the idea is there. Right? I'm not saying it's always the reality that they will always let you have the machine, but the reality should be that they would, right? But they don't always do that. But if you have a schedule, you can give that schedule weeks, months in advance and say, look, here's when I need it, here's how long I need it, here's what we're going to do, here's the parts, the manpower I need. Everything can be forecast, budgeted, and accounted for. It's a very nice way of doing things. The downsides, though, are you're spending a lot more money all of a sudden on these parts and labor. You're also potentially throwing away parts that do have remaining useful life. So you're giving up some of the life of the parts. Now, as we said, of the common probabilities of failure, infant mortality was one of them, and you're just now introducing a whole lot more of that. So there's sometimes an increase in the number of failures due to applying preventive maintenance practices, even though overall you might see a decrease in the downtime or the costs associated with failures. But the most important factor is you're never going to completely eliminate failures. No matter how aggressive your schedule is, no matter how much maintenance you do ahead of time, it doesn't mean it still won't fail. It just won't fail through, things like wear out or other types of common failure mechanisms. But you could be, as I said, introducing a lot more infant mortality. So we have to be careful how we balance these things. So where we think we're getting better is to move up to predictive maintenance. And this is also known as CBM, condition-based maintenance. And this seems like where a lot of people strive to be, is they want to replace parts or do maintenance on machinery as it's truly needed based on some types of measurements. So this is where you have to take measurements. That's the key thing about predictive maintenance or CBM. Measurements are performed somehow. Could be temperature, could be pressure, could be infrared, could be oil analysis, vibration, right? Anything. Some type of measurement that you track and you use either trending or thresholds or something like that to determine this is now on a path to failure. So when you do this, Typically, you do this on your most critical assets because this is going to be, of course, even more expensive as an initial outlay. But going back to the NASA document, is in fact predicted to be even cheaper than preventive maintenance, which was cheaper than reactive maintenance. So this is supposed to be the most money-saving option of them all. And the big advantages to doing condition-based maintenance is that you're not spending as much money on parts and maintenance because you're only doing it where it's necessary. But because you have predictions as to what's going to happen here, you should have a decrease in downtime because you know beforehand that it's on its path to failure. The downside being it's going to take a lot more of an initial investment to get there because you're going to need to buy whatever the diagnostic tools are, a FLIR camera, a vibration analyzer, an oil analysis program, whatever it might be. And then you need the people to collect the data, and then you need the people to interpret the data. And there's a lot that's involved here. So a lot of costs, initially at least, go into this. But once again, it still will never completely eliminate all failures. There's certain types of failures that occur so rapidly that they can occur between two successive measurements, meaning you can take one measurement and everything looks fine, but by the time you go to take that second measurement, it's already failed. And so you think, well, maybe I should just start taking my measurements more often. Again, it's sort of balancing the cost of all these things. There's only so much you can do before it becomes overkill in so many other areas, and it just doesn't outweigh the benefits you might see in one small area. So we have to be cautious with this one, that it's not necessarily the be-all, end-all solution. But while we're on the topic of performing measurements, let me just take a quick little side break here and mention of the four main diagnostic tools, each one has a couple of areas where it can do things that the other three generally doesn't do as well. So oil analysis is far better at predicting wear, contamination, and above all, lubricant degradation than any of thermography, vibration, or ultrasonics. However, on the other hand, vibration and ultrasonics can pick up misalignments and imbalances far sooner than oil analysis or thermography would. So it's things like this is how you interpret, this slide here. But my point is that each technology has some advantages and some disadvantages. And when you try and create a program, you'd like to fill in as many of these gaps as possible so that you've got all the advantages and very few of the disadvantages. And the two technologies that mate together very, very well are both oil analysis and vibration. And this is an excellent paper from the folks over at the Palo Verde Nuclear Station. And they summarized where they thought the strengths and weaknesses were of each technology as they used them at their facility. And if you look down at the third line where it says machine unbalance, that is something they did not feel lubricant analysis really could address, but that was definitely a strength of vibration analysis that you could detect an imbalance within the first few rotations of a piece of equipment. On the other hand, on the next line, if you had contamination in the oil, like say water, vibration wouldn't pick that up, right? Not until the damage was already so far gone that it caused even greater issues, but that's a strength of oil analysis. So they saw this balance between the two, and of the machines that they monitored, which numbered up to about 750, as you can read, they felt nearly 2/3 of the failures could be caught by oil analysis and oil analysis alone. On the other hand, only slightly fewer failures could be caught by vibration analysis and vibration analysis alone. But they saw nearly 1/4 of the failures were needing both technologies to be able to predict the failure, meaning they needed both the oil analysis data showing something and the vibration analysis showing something to definitively say, yes, we think that's going to fail. So that's why this chart adds up to over 100%. There's a bit of a synergy that's going on here where you can see that, yes, we need two technologies to really leverage and promote, good finding of potential failures. Now, if you're into statistics, I have one more quick slide for you. It was NASA's take on this, just showing some of the benefits of going to predictive maintenance. They said the ROI on it was about 10 times. The reduction in maintenance costs was fairly significant. The number of breakdowns was the majority. Downtime was not quite as much because, again, a breakdown doesn't always equal a lot of downtime. And then production went up, sort of commensurate with maintenance costs. So definitely some advantages here, but I think the easier way of sort of looking at everything that we've already looked at is summarized best with this graphic. If you're looking at overall costs, you have to balance what we would consider to be a maintenance cost, the money you're spending keeping your equipment running, with the operational or downtime cost, the money that you have to spend when things go wrong. So when we think of reactive maintenance, we're spending almost nothing on the actual maintenance costs, but we are suffering in the downtime costs. So that's why the orange is high and the blue is low. If you go to the flip side, though, preventive maintenance is kind of the opposite. We're spending a lot more on maintenance, but we're not suffering as much in operational or downtime costs. However, the overall cost is very similar. Where we see the true benefit is when we go to predictive, because with predictive, we're trying to balance just enough maintenance costs to keep just enough of an operational or downtime cost. So we're not eliminating downtime as much as we might be with preventive maintenance, but we're certainly not having to spend as much money, and the sum total is significantly less. So the aggregate cost is what you're seeing in the gray line there, and you can see how it's got a nice dip to it in the middle. And a lot of people ask me, because they know we're working our way towards proactive maintenance now, they go, where would proactive maintenance fit on that same chart? And they go, is proactive maintenance exactly where those two lines, the orange and the blue, intersect? And I would argue that it could be there, but proactive really tries to grab that and pull it down even lower. It tries to find the lowest of the lowest costs for both maintenance and for downtime. So with that, we should talk about proactive maintenance then. So it's commonly referred to as failure avoidance, which I know might at first sound like preventive maintenance, because with preventive, you're arguably avoiding the failure because you changed the parts beforehand. But we're saying no, we're avoiding the failure altogether. It is never, ever, ever let it fail the same way twice, right? It is, so basically it says don't let it fail, but if it fails, don't let it fail the same way again. So we're trying to do things to prevent failures as best as we can, but when it fails, we do as much as we can to learn from that failure to make sure it will not fail under the same circumstances again. So that's where you see the acronyms like RCA, where we talk about root cause analysis, or the 5 whys, or failure modes effects analysis, or failure mode effect and criticality analysis. Some people put the C in there, some people don't. But one of these tools, one of these acronyms is a way of getting to the root of the problem, right? That's why root cause analysis is one of the more popular terms. So you're trying to figure out what was the initial driver to that failure, and how can you eliminate that as a driver going forward. So again, you still have to suffer a failure, but it won't fail that same way again. It doesn't mean it won't fail again, it just means it won't fail the same way again. So kind of critical that we understand that again, proactive maintenance doesn't mean failure avoidance as in you avoid all failures. It means you just avoid repeat failures. So the big advantage with proactive maintenance is that you're going to reduce the severity of your failures, because every time you have a failure, you're going to make sure it doesn't happen again. It probably will fail still eventually, but it should fail under a much less severe condition. The disadvantage, though, is that every time there's a failure, instead of just swapping out the parts real quick and putting it back into production, you're going to have to perform what's usually called a post-mortem or an autopsy or a root cause investigation. It goes under a variety of names. Basically, you're going to have a lot of questions, and you may need to see the parts of the machine in situ as it was. You may need to ask a lot of questions before you can remove it. Basically, it's like a crime scene, right? You don't want to remove the evidence until you've classified everything properly, and then you can remove it and continue your investigation at a rebuild shop or however you have to do it. But it is very intrusive, and to this end, it means that not a lot of people are keen to let it happen because, of course, production is money. So it seems like a great idea, but it's much harder to implement than it might appear on the surface, because it sounds great to say, hey, let it fail and let's learn from the failures. On the other hand, nobody likes to be asked questions about what did you do just before it failed. What was the last time you checked it? When was the last time you did this? And it feels very accusatory. So you get a lot of defensiveness when you start doing these kinds of things. But if it happens, you'll learn a lot and you can help deal with this. So my analogy to help bring all 4 of these into focus so you can understand all 4 from the same perspective is this. Think about tires, right? if you have a tire and it goes flat for whatever reason, right? You run over something, doesn't matter what it is. But if you fix or replace the tire, that was reactive maintenance that you just performed, right? You reacted to the failure. The tire had to fail first, and then you reacted to it. Now, preventive maintenance would be if you bought tires rated for 60,000 miles, and at 60,000 miles, you simply swapped out your tires, right? You're not going to have a wear-out problem in all likelihood, but doesn't necessarily mean you didn't have a flat somewhere along the way. So it's a schedule, right? That's when we said time or schedule-based maintenance, but doesn't mean you necessarily removed all failure types. Now, predictive maintenance would be doing some type of measurement. So that would be replacing your tires based on, say, something like tread depth. So you check your tread depth every 10,000 miles, and you're expecting that as you get towards 60,000 miles, that you're probably going to need to replace your tires. And maybe you'll start checking a bit more frequently around that time. But you're not going to change your tires until you stick your penny in the tread and you can see the top of Lincoln's head there. Right? That's your little tip for how to check a tire. So it is measurement-based. That is the form of predictive maintenance. Proactive maintenance, though, would be this. It would be buying tires rated at 60,000 miles. It would be planning on changing them at around 60,000 miles. But you have learned from past experience that your tires wear out faster if the pressure is low. So when you're out there doing your tread depth checks, you also add in a pressure check. And that helps you collect more data and helps you avoid a situation, right? Why we call it failure avoidance. Avoid a situation that will lead to the tires prematurely wearing out. Now, again, you might learn over time that if you don't rotate your tires, your front tires might wear out more frequently than your rear wheel tires. So you rotate your tires when you do your tread depth checks and your pressure checks. But then you might also learn from experience that if your tires are ever misaligned, they wear out more prematurely than if they're properly aligned. So then you add in an alignment, right? Every time you learn something, you now apply it to every tire going forward, and you're avoiding the same failure mechanisms. Now, the tires will still wear out. The tires may still have a flat, but you're learning from past failures what to do to avoid a repeat. That's proactive maintenance. So with these, as I said, NASA was in their document saying preventive was cheaper than reactive, and predictive was even cheaper than preventive. They had no commentary on proactive, but I did find this particular set of data from Pump Magazine, and they published in terms of horsepower per year, how many dollars it takes to do the maintenance, and they came up with the same conclusion that reactive was the most expensive and proactive actually was the least expensive. So even though it's very, very intrusive and all that, overall your costs are lower. Now, what was interesting, going back to that NASA document, was they did a survey in the industry, and they asked people, what type of maintenance are you doing? And the resounding answer was reactive, right? Obviously, the more expensive way of doing things. But the other interesting thing, this quote that I'm showing you here, was that too many people think of maintenance as the repair that you do after the failure. And if you get right down to it, maintain means to keep, the steady course. Maintain means to keep it running. So repairing something is not a form of maintenance if you want to get into the semantics of what the word means. And so they felt that really reactive cannot be classified as a form of maintenance because it's not maintaining squat. It's returning things to service after repair. But I'll let you argue that if you like. But it's kind of an interesting perspective to say that, yes, largely following reactive maintenance as a strategy is not really any strategy at all. It is not really any form of maintenance either. But anyways, this gets us through the core information, sort of the base that we need to discuss RCM. And RCM is maybe not as new as you might think, and probably older than most people even realize. So let's start our history here, timeline. And the very first occurrence of RCM is commonly believed to be in the 1970s, but there's evidence of it having occurred significantly earlier. And one of the best examples was here in 1943. The Royal Air Force, so Britain's airplanes, during the Second World War were tasked with sinking U-boats, German submarines. And they weren't being that successful at it, so they hired one of their own scientists, and go figure this logic, an embryologist, so a guy who studies embryos, the unborn. But he was a scientist. He applied the scientific method to his task here, and he came up with a couple of really good conclusions. He said, look, to successfully sink a U-boat, the plane has to drop a bomb and predict what depth the submarine will be at, so the depth charge will go off accordingly. And he said, to properly predict how deep the submarine will be, you need to know when the submarine's going to spot you, because as soon as it spots you, it'll dive. And if you know that, you'll know the rate at which it descends, and you can figure all this out. He said that we could do this a couple different ways, but one of the other things we needed to do was to try and reduce the depth as much as possible. So the easiest way to do that is to not be seen so soon. So the two changes that he made was, one is that he changed the paint scheme of the underside of the airplane. So if you're familiar with World War II aircraft, you might know that the top of the airplane, if you viewed from above, was typically painted in some sort of camouflage coloring, but the bottoms of airplanes ended up painted very light colored, so they would blend in with the sky when viewed from below. So the U-boats couldn't see them as early, and it was something in the neighborhood of they got about 30% closer before they were detected, which narrowed the window of opportunity for the dive. So that narrowed the depth that they would likely be at when the bomb was dropped. So this guy, Waddington here, redid the calculations, adjusted the depth charges on the bombs, and they got something like in the neighborhood of 70% uptick in the number of U-boats they were sinking. So while this all sounds very interesting, I'm sure you're wondering, how does this have anything to do with RCM? So basically, after he completed his task, he tells them the secrets. And of course, this is during the war, so everything's suppressed. You can't publicize this in any way, because then the Germans would figure it out. He says, you'd sink a lot more U-boats if you made one other change. And, being that he's already improved things so much, they're like, yes, we're all ears. What else have you got? And he said, really, one of the reasons you're not sinking as many U-boats as you'd like is, he said, you don't have more than half your fleet flight ready. He said, every squadron I visited, now squadron was typically 40 aircraft, he said, about 20 of them are flight ready. He said, the other 20 are in for maintenance all the time. And what he observed was, and we have a new term for it now, but what he observed was every 50 hours, they had an on-schedule maintenance. Now, in today's world, we call this a PM, right? A preventive maintenance schedule. So that every 50 hours you do a PM. In the first 10 hours after the PM, the stack of work orders is enormous of all the things you got to follow up on. After 20 hours, it's a little bit lower. After 30 hours, it's even lower. And after 40 hours, it's really low. But then you hit 50 hours and it goes in for maintenance again, and the stack of work orders increases again. And that's where you get the quote you see there on screen. He said that doing these PMs, doing these scheduled maintenance activities, he said tended to increase the number of breakdowns. And he said, this is not good. He said, I'm paraphrasing now, but he said, leave it alone, stop futzing with it. So this was very interesting, because it was a revelation to the world of maintenance, but it was during the Second World War and it was suppressed. So nobody found out about this. Now, fast forward a little over 15 years, and we're dealing with the civil, civilian aircraft, and they formed this industry task force group to look at how good were preventive maintenance activities, PMs, as I just called them. And they came to their conclusions that they weren't very good, and they should do something that at the time they called on-condition maintenance. So they gave it a new name. And what that spawned was a maintenance steering group that created this landmark document for how to maintain a 747 aircraft, which a couple of years later, they formed a second one, and it wrote documents up for the DC-10 and the L-1011, which were also very popular civilian aircraft at the time. And before we get too far into the timeline, let me show you examples from these documents. So this industry task force group in 1960, they said scheduled overhaul PMs, not very good. And they, of this, really, unless there was a dominant failure mode, unless there was a constant way it failed, no way to do maintenance in a viable way. The other conclusion they came to was they said there were many things doing maintenance, any form of scheduled maintenance, not effective. So what this led us to was the steering groups writing up their documents to try and eliminate all the unnecessary maintenance and all the PMs that weren't really being that effective. And just to give you a couple of examples here, The DC-8 was an aircraft not included in the maintenance steering group's activities, and it had 339 assets that required overhaul. After they performed this task on the DC-10s, they narrowed their list for DC-10 down to 7. Right? It just shows you how much redundant work or unnecessary work was being done that really had no positive effect on the overall reliability of the aircraft. The other example, the first steering group worked on the 747, and again, comparing it to the DC-8, the DC-8 needed nearly 4 million man-hours to get 20,000 hours of flight, whereas the 747, they narrowed that down to 66,000 hours of maintenance to get the same 20,000 hours of service. So, like I said, very revealing to industry just how much maintenance wasn't giving us a net positive effect. So this started to stir things up, and where it stirred things up was with the military. So the DoD commissioned United Airlines and said, look, you guys on the civilian side, take a look at how you're doing things, see if you can come up with something better, and we'll implement it on our side. So over the next bunch of years, United Airlines worked on this, and that's when they published that landmark report, the Nolan and Heap report I was talking about earlier. It's actually called Reliability-Centered Maintenance. And if you Google that particular report number there, you can download that as a free PDF, because of course it's now in the public domain being a DoD document. Fantastic document. It's a bit long though, but it had some really, revolutionary thoughts in it. So once this was published and it became known to industry, well, then we had another guy come along and start changing things up. So Maintenance Steering Group came out and they took this and they ran with it. And they reorganized all those documents they'd previously written. And over the next few years, they basically went through another 9 revisions to those documents, further and further reducing the maintenance where it was not required or did not have a net positive effect, and really shook things up. So let me give you a couple of quotes out of that Nolan and Heap document just to show you how things happened. So they uncovered 2 myths. Now, the first myth is that components could be retired or overhauled before they failed. Right? You could perform preventive maintenance as myth number 1. And the quote from the document says, over the years, it was found many types of failures could not be prevented no matter how intensive the maintenance activities. So meaning, really, the best thing to do would be to run it to failure. The other myth they uncovered was the likelihood of failure increases with age. And it said, despite the time-honored belief, so on and so forth, that it was ineffective at controlling failure rates. So PMs were not effective. Right? PMs didn't prevent things from failing, and PMs didn't happen, failures didn't happen according to the wear-out curve. Right? Like I said, they found infant mortality was really the largest factor. So once they sort of uncovered these 2 myths, that really 2 parts of the bathtub curve just didn't apply, they sort of came back to it and said, well, where this is stemming from, and you can read the first quote here, but the first quote basically says, we don't know what a failure is. So they throw around the term failure to things that cease functioning. And they said, that's not good enough. A failure, and you can read the second quote here, is an unsatisfactory condition, meaning a failure can be anything that simply doesn't work the way you want it to. It doesn't last as long as you want it to, doesn't have as high output as you want it to, doesn't have the efficiency you want it to. Whatever it is not functioning the way you desire it to function. So with this, they came up with a suggestion for 2 different definitions for the term failure. So they said a functional failure is when, it stops working. That's the classic definition of a failure. And that, of course, is usually identified by the person operating it. They go, hey, it's not working the way it should. On the other hand, they said a potential failure is the first sign that it will ultimately lead to a functional failure. And that is this kind of stuff found by the maintenance technicians. So this is what spawned, if you take those 2 words, functional and potential, rearrange them, put potential first and functional second, that's what created the PF curve. So with the PF curve, they said, look, there's a condition to every piece of machinery, and it starts nice and high, and it deteriorates over time, but at some point, there'll always be an inflection, a no turning back point, where once it surpasses here, it's going to eventually go to a complete functional failure. And so they defined this interval between when you could first detect it and when it would ultimately fail as the PF interval, named after the potential and the functional failures. Now, here's where it gets a little bit interesting for folks who've seen the PF curve, 1,000 times on social media, is that almost everybody who publishes a PF curve is trying to sell you something. And usually what they're trying to sell you is something to figure out when P is going to happen, right? They're selling you some condition monitoring technology. And the thing they most often get wrong is not necessarily the order that everything appears in, it's where the P goes. Because the idea is, and this is the oldest example I can find, this is the most classic example from the Nolan and Heap report, is that you're never changing when F happens. All you're trying to do is figure out P sooner. So when we talk about extending the PF interval, we're not pushing F out to the right, we're pushing P to the left. And this is just what the original curve had for suggestions as to which technologies were the best, that oil analysis was among the leading indicators, followed by vibration, whereas things like thermography, and if it ultimately led to noise, which would be a form of vibration, or heat, which could be detected by FLIR, that was much later. That's not always the case for every type of failure, and like I said, don't get too far into what's labeled on the chart. Just understand when we talk about PF intervals and improving them, we're not talking about moving F. F will happen when F happens. P, on the other hand, if we can figure out P sooner, we can plan for it better, and we can extend our maintenance activities as best as possible to be as low a cost and as low impact as possible. But F will happen. So moving along our timeline, just to finish it up here, after this was sort of realized, another book called exactly Reliability-Centered Maintenance came out, and this is kind of the Bible of industry. John Mowbray's book is considered one of the best in industry, and I'll show you one quote from that. Another document that came out a few years later, this one here, the SAEJ A1011, is a terrible, terrible document to follow, very hard to follow. I'll show you an example of that. Then NASA published the amalgamation of a lot of RCM knowledge and data into that one book I've been quoting from extensively throughout this presentation. But thankfully, a couple of years later, the SAE JA1012 came out, which was a user guide to the JA1011 to make it much more usable, so it wasn't such an awful document anymore. And I'll show you an example out of this one. But essentially, when we talk about RCM is not a fifth maintenance strategy. It's not a new maintenance strategy, but rather it's a reorganization of all existing strategies. And one of the things it does, if you've heard this term before, it's either called the Pareto principle or the 80-20 rule, meaning that 80% of the problems come from 20% of the causes, or something along those lines. You can paraphrase it however you want. But we recognize that most of our problems come from the select few, and therefore we need to treat the select few differently than we treat the remaining bunch. So the best way of kind of summarizing all that into one thought is John Mowbray's definition of RCM. And again, I'll paraphrase it so I'm not reading every slide here, but he basically says RCM is doing whatever is necessary to make it work the way you want it to work. And if you're happy, this is the point, if you're happy with it running the way it is, and you're getting the life that you expect, you're getting the costs that you're happy with, and run it to failure. That's fine. That's RCM. If you consciously make that decision, that's RCM. So as an example, in your own house, light bulbs are something you absolutely run to failure. But you've done RCM on this. You've decided that you'd rather deal with the odd bulb burning out than it would be that every 2 years you go and change every single light bulb in your house to try and prevent the failures. Right? You're throwing away perfectly good light bulbs by doing that. You're not preventing all the failures, and it's very costly to replace all the light bulbs in your house in one go. So you've collectively decided that, yes, I will run my light bulbs to failure. Now, on the other hand, you might decide that, yes, I'm going to change my furnace filter every 6 months, whether it needs it or not, because then it gets done. So you're deciding the preventive schedule is exactly what you want, and that's what you do. On the other hand, if you look at your HVAC system, you look at the burner inside your furnace, well, you're not going to replace your burner every 5 years just because. So you might call in somebody every 5 years to give it a check. And if they see that it's in good condition, there's not significant rusting, and they give you another couple years on it. You say, okay, I'll call you back in a couple years. You check it again then, and they come back in a couple years and check it again, and then tell you, okay, yeah, it looks like maybe it needs replacing, and then you decide to replace it. Well, you've done a form of predictive maintenance on that because you decided that that was the best way to spend the money and the effort towards that side of your HVAC system. So I can give you countless examples, but again, RCM is simply deciding to do whatever you feel is necessary, and you're choosing essentially one of the first 4 maintenance strategies. Now, this JA1011 here, this is, like I said, a terrible document. It's hard to follow, but basically there's 7 questions. If you can answer these 7 questions as they apply to an asset, it would help steer you into the right maintenance strategy for that particular asset. Let me show you the 1012 in 2 slides and you'll understand this a bit better. But here's how I think you can summarize RCM best as possible. Like I said, RCM is not a 5th maintenance strategy. It is not the same as proactive. I know some people think that proactive and RCM are kind of the same thing. It is choosing which of these 4 to use when. And this NASA document I've been quoting from had this nice summary here to show you how do you typically decide which strategy to use on which type of asset. So on the one hand, starting on the left, if it's a very small, non-critical, inexpensive, inconsequential item, you should probably just run it to failure, right? And in your own household, that's things like a toaster, right? Nobody does maintenance on your toaster other than dumping out the crumbs, but you're not checking electrical connections or doing anything like that. You just run the toaster. When it suddenly fails after 20 years or whatever it is, you just go buy a new one and you just didn't have toast that day. On the other hand, proactive maintenance, going to the far right, proactive maintenance would be the exact opposite. It would be generally the larger items, the ones that are critical, the ones that do have consequence, and the ones that maybe are a bit more likely to fail. So proactive maintenance, for those of you who have a hot water tank, right? If you've ever had a failure on the hot water tank, you've probably learned from that failure that one of the ways to extend the life of your tank is to drain it on occasion, flush out all the rust and debris that builds up on the bottom. So you start implementing that as a once-a-year thing that you do. It's not preventive maintenance because you're not replacing the entire hot water tank every year or every 10 years. You're doing this yearly preventive activity, which, like I said, is actually being more proactive. But you're learning this from a past failure, that this is something you can add to extend the life to prevent the same failure again, or at least the same rate of failure again. And you're thinking it's much more consequential to your life because nobody wants to have a cold shower that day, and you can't always get a new hot water tank the same day that you have the failure. So it does cause some significant downtime. It is an expensive item in your household in terms of maintenance activities. So you typically, like I said, do it on completely the opposite things. Now, the 2 in the middle, preventive and predictive, basically can be summarized as, does it or does it not have a predictable failure rate? If it has a predictable failure rate, as in subject to wear out, as you can read there, then you will put it on a preventive schedule, right? If your furnace filters typically don't last more than 6 to 12 months, then yeah, you replace them every 6 to 12 months. But on the other hand, if it's got completely random failures to it, you have no idea from one to the next whether or not it's going to fail, then you should put it on a predictive schedule so that you've got measurements being taken to help guide you that way. But this chart does a nice summary, I think, of showing us the way that all the technologies work and how to choose one over the other. The JA1012 is, like I said, the user guide to the previous 1011. It's got the same 7 questions on here. They're just structured into a flowchart method. Makes it a bit easier to follow it and makes it a bit easier to see where you come out in the end. But in summary, RCM really has the best advantages of all and the least costly disadvantages. It's got the lowest parts of maintenance costs because you're doing things when they need to be done and only when they need to be done and if they need to be done. You've got better efficiency and reliability because now you're preventing those catastrophic failures from occurring again and again. You should have a decrease in the sudden or catastrophic failures, but you may not actually have a decrease in the overall number of failures. You still just have failures, but they're to a lesser degree. The disadvantage is it's one of the most costly to get set up and running because you're going to need a lot of diagnostic tools, much like you would for predictive maintenance, but you're going to need a lot of training and all that to understand the data and look for the patterns and not just try to predict the next failure, but kind of look backwards in time and say, okay, how could we have seen all these? How can we predict the next ones? What can we do to prevent them? How do we be proactive? All that kind of good stuff. My last point, though, is the perceived value is not always easily seen. What's funny is those who get really good at RCM end up with very well-running plants, and then people start looking at this, and one of the first things they try and cut are maintenance costs because they go, well, I guess we don't need the maintenance department anymore because we're not having the failures. And you go, no, it's because of the maintenance department that we're having fewer failures. We need everybody on staff. So that gets a bit tricky to fight. The last little statisticky thing I'll leave with you is this one. People love to see this one because it shows that there's not a quick return on investment when it comes to implementing an effective maintenance program. Basically, you're trying to get away from all the planned PMs and the reactive maintenance, and you're trying to migrate towards condition-based or proactive-based maintenance. That would be the overall lowest cost, but it takes a couple of years minimum. That's what we call an investment period, where you're actually going to spend a bit more money getting there. And once you reach that break-even point, everything after that will be profit. And at that point, maintenance is no longer a cost, it's a savings. But people like this graphic because it shows that just because you buy a FLIR camera, just because you buy a vibration analyzer, doesn't mean you're going to have enough saves in the first year to pay for the program. So there you have it. So to summarize the entire presentation, just understand that no single maintenance strategy is the best one to apply to all assets, right? It's better to apply a balance and pick it, even if they're assets of the same type, you might go, look, that one's reliable, this one isn't. We're going to do two different things here. Also understand you're never going to avert all the failures. What you're hoping to do is not necessarily reduce the number of failures, but at least reduce the severity of the failures. So the failures are less intrusive and costly to you. RCA will be the key at preventing the repeat failures, but it doesn't, again, always necessarily remove the failure completely. It just means it won't fail the same way twice. So with that, I've hit the hour mark almost exactly. I'll turn it over now for any questions, but I do thank you for taking the time to watch us on this afternoon, and you have yourselves a good day.
Yes, Evan, thank you. That was great. I'm going to limit us to just one question in the interest of time right now. But we did have a question about if we can extend the P point by investing in capital expenditures such as proper alignment and installation. Can you comment on that a little bit?
That's not really what's meant by extending, the PF interval. Certainly, it helps at preventing the failure. It is a form of proactive maintenance. So it's really looking at trying to, if I was to pick a term, and I'm not happy with this term, but really what doing things like alignments and balancing would do is extend the what we call MTBF, the mean time between failures. But that is a term that not everyone likes. Some people choose to measure it, others don't see the value in it. I'm kind of in that second category where I'm like, okay, not everything fails the same way twice or fails the same mechanisms. So it gets a bit tricky, but no, doing an activity like that is a form of proactive maintenance, which isn't really the heart of the PF curve, is more on condition-based maintenance. So I wouldn't see it as the same thing. I understand why it's perceived that way, because it, of course, improves the running of that machine, and it seems like it pushes F further out, but the PF curve is more about the condition, the P, so that's what it's intended to represent. So I guess that's kind of your answer there, is no.
Okay, thank you very much for that. Everyone, thank you again so much. This recording will be made available to everyone. If you have any additional questions, please feel free to contact Evan directly. His email address is right there. And you can always find out more information from Test Oil and check out our blog as well. There's an upcoming webinar calendar. We always have training classes available as well for you. And otherwise, we'll be in touch to get your additional questions answered over email. Everyone, take care and stay safe. Thank you.